Now we understand the basic properties of optical waveguides. Next, we shall discuss common techniques to couple light into and out from the waveguides. We shall go through three techniques: prism coupling, end-fire or butt coupling, and grating coupling. Here we have a slab waveguide, and now we shine light from top. Light refracts, reflects, but doesn't stay in the waveguide by total internal reflection. The fundamental reason for this is that the wave number in the cladding is always smaller than the propagation constant in the core of the waveguide. Therefore, the wave number of light, and especially its tangential component, needs to be increased to enable coupling of the incident wave to the propagating waveguide mode. This can be realized either by a prism, a diffraction grating, or scattering. By inserting material with higher refractive index on top of the cladding, we can increase the wave number of the incident wave. Now, the tangential component of the field is phase matched with the propagation constant. The field extends from the prism to the waveguide by an evanescent wave as a result of the total internal reflection. In the waveguide, it couples the incident light to the waveguide mode. From the phase matching condition, we can write a coupling condition as the tangential component therefore equals the propagation constant. Let's take an example. Our waveguide has a refractive index of 2.0. The claddings have refractive indices of 1.7 and 1.0. For this waveguide, we have calculated the effective indices of 1.9594 for the fundamental TE mode and 1.8375 for the second order mode. Now we select a prism with refractive index of 2.5. From the coupling condition, we can now calculate the angle which is needed to couple the desired mode. The first mode is coupled at an angle of 51.6 degrees, and the second mode is coupled at an angle of 47.3 degrees. Here we have a practical realization of prism coupling. When we measure the reflected signal, coupling to the waveguide modes are seen as dips in the reflectance. Here we see that the first order mode is coupled at an angle of 51.6 degrees as we calculated, and the second mode is coupled at an angle of 47.3 degrees as we also calculated. Therefore, this technique enables to map the effective indices of slab waveguides and also selectively couple incident light into a desired waveguide mode.